this lecture, we're going to cover refraction and Snell's law. So in order to talk about refraction and Snell's law, one thing we have to understand is that as light travels through a vacuum, it travels at the speed of light, which is 3 times 10 to the 8 meters per second. Light is the only wave in the form of a transverse wave that can travel through the vacuum of space, whereas sound waves cannot. Sound waves actually have to have a physical material to vibrate, whereas light rays are electric and magnetic induced fields that oscillate back and forth and induce the next field. So it's a combination of what we learned in electrostatics and what we learned in magnetostatics that brings us to light and radiation. Now, when we talk about electromagnetic waves, which is light, when it goes through a material that's more dense than air or a vacuum, it actually slows down. And that's because the particles interfere with its movement, and that ends up causing it to slow down. It's sort of like going from walking on a sidewalk to walking through a muddy field. Okay, you start to slow down because you get kind of stuck in it. Okay, so in order to determine how much stuckness we have a quantity called the index of refraction. So let me go ahead and highlight that for you. Right here is the index of refraction. It has the letter n, lowercase n, to represent that value. It's actually the ratio, here you go, the ratio of the speed of light in the vacuum to the speed of light in the material. Okay, so that's how we determine the index of refraction. The index of refraction should be 1 in a vacuum. It's close to 1 in air at standard temperature and pressure. And as you can see in the chart, it's 1.0003. We usually only go to 2 digits after the decimal place for our precision. So in essence, a vacuum and air have about the same index of refraction. For water, notice it's 1.33. It is greater because the index in air is faster than in water. Ethyl alcohol, 1.36. Notice for glass, there's different types of glass. Fused quartz is 1.46, crown glass 1.52, light flint is 1.58. Diamond, notice, is 2.42, plexiglass or lucite 1.51. Okay, so when you're looking at these numbers, they represent the ratio of how fast you can go in a vacuum versus how fast you go in the material that you're in. The larger the number, the slower the light goes. Okay, so light also changes its direction when it enters that new material. This is what we call refraction. The incident angle is no longer equal to the refracted angle. It is equal to the reflected angle, but not the refracted angle. The refracted angle is the angle of the bending as it goes from one material to another, such as going from air to glass or from glass to water. So when the light ray goes from a less dense material to a more dense material, it's going to bend toward the normal, and the refracted ray is going to be smaller. You have to know this. If you don't know this, it's going to make it really difficult for you on any type of test or any type of multiple choice question they might ask you. Okay, so this can come up in the free response. It's really just something you have to memorize. When you go from a less dense to a more dense, you're going to bend towards the normal. When you go from more dense to less, you bend away from the normal. Okay, so from less to more, toward. When you go from more to less, away. Okay, so notice here that as the light ray comes in, there is a reflected ray. That angle of reflection is the same as the angle of incidence. So this is theta 1 here. As the light ray goes in the material, notice that it is refracted. This refracted angle is going to be less than the incident angle because you're going from air to water. Okay. If, though, you start from water, here, notice that we have N1 for water, N2 for air. So if we go from N1 water, and notice again, here's your reflected angle, which is also equal to theta 1. As you go from water to air, the angle gets larger. Notice that the refracted angle here is the same as the incident angle here. Okay, they have to be. The ratio of the angles, the signs of the angles, is going to be the same. All you're going to do, though, is flip which direction. So notice the picture looks identical, except that the angles are different, and your reflected ray is in the opposite material. Okay, so in order to find that relationship, we're going to be using Snell's law. So this is Snell's law. Snell's law says that N1 sine theta 1 is equal to N2 sine theta 2. I always make N1 where I'm coming from and N2 where I'm going to. And it kind of rhymes. 1 from, 2 to. Well, it's two different 2's, but you get the point. Okay, so theta 1 is where you're coming from, theta 2 is where you're going to. Okay, and so notice that if I were to draw this light ray going straight through, this is the original path. Notice that it bends towards the normal when you go from less dense to more dense. Okay, here, notice if I were to go straight through, oops, moving my diagram here. Okay, notice here if I were to go straight through along this line, it's bending away from the normal. The angle is further away from the normal line than the original ray would be if it went from water to water. Okay, so you can see that this one bends away from the normal, this one bends towards the normal. When the light passes from air to a different material and then back to air, the light ray that enters the medium is parallel to the light ray that exits the medium. It's just going to be shifted. And there's a linear displacement of that light ray because of it going from air to glass to air. And this is why when you see that picture of the Barbie doll that looks like she's cut in half when she's in a glass of water, that's essentially what's happening. The light rays are coming from the Barbie doll, they're hitting the glass, they're bending as they go through the glass, then they're bending again as they go from glass to air, and it causes a shift, a linear shift of those light rays. So using geometry, we can find the linear displacement between the emerging ray and the incident ray if we know the angle of the incident ray and the thickness of the material. Okay, so by knowing those things, you can find out how much that shift is. So again, this is why objects look weird if they are partially underwater. And here you can see that the straw comes out here, but here we see it over here, and it kind of looks like it's, you know, shifted. If the incident angle is just big enough, the refracted angle would be parallel to the surface. So the refracted angle will be 90 degrees. We call this angle the critical angle. So this only happens, though, when you're going from a more dense material like water to a less dense material like air. Because remember, when you're going from more dense to less dense, it bends away from the normal. Okay? In order to get that 90-degree angle, which we see right here, 90-degree angle, our critical angle, or this angle here, this incident angle, has to be equal to the arc sine of N2 over N1. Okay, so that's how we determine the critical angle in order to have the light ray travel along the surface. Anything greater than the critical angle will cause total internal reflection. So when the light ray of incidence, or when the angle of incidence is larger than the critical angle, no light will escape. Okay, so here we have a normal angle, theta 1, right here, and this is theta 2. Notice theta 2 is greater than theta 1. Here we have the critical angle, and notice that our refracted angle, theta 2, is equal to 90 degrees. Notice here that this angle here is greater, so this theta 1 is greater than the critical angle, And notice we end up with total internal reflection. Remember that light both reflects and refracts when hitting a surface. For example, see what happens to the light ray as it goes from glass to water to air. So first, here is our incident ray. It starts here in the glass. It hits the water. Part of it is refracted, part of it is reflected. This reflected light comes straight out of the glass. The refracted ray is going to reflect on this boundary, so part of it's reflected and part of it is transmitted. As you go from more dense to less dense, it's going to bend away from the normal. So notice that refracted angle is greater than the reflected angle. Or I'm sorry, the incident angle. Now here, this is the reflected beam. Part of it is going to be reflected again, and part of it is going to be transmitted. Okay, and it's really easy to see this with a beam of like a laser beam. Then you can really see all of these angles taking place as they go through a piece of shiny glass. So I'll see if I can pull up a YouTube video, or I'll see if I can pull out the laser and a piece of glass so that you can see this effect. Okay, so here's question 8. A ray of light bends blank when going from air to glass. Toward the normal, away from the normal, not at all. Okay, so let's check your answer. Hopefully you chose A, toward the normal. A light ray incident on the surface of glass is shown below. Which of the following represents the refracted ray? Okay, so here is your incident ray here. Which one is your refracted ray as you go from air to glass? Okay, because you're going from a less dense to more dense material, it should bend towards the normal. So hopefully you chose D. D is the correct answer. A ray of light passes from water to air at the critical angle. Which of the following shows the refracted ray? Okay, did you choose B? That is the correct answer. A light ray passes from substance A to substance B and exits substance B at point P. Where would the ray exit if the substance B was replaced with a material that has a lower index of refraction? Is it above point P, at point P, below point P? The location cannot be determined without knowing the two indices of refraction. Okay, so let's see what the answer is. The correct answer is C. It will be below point P. A substance has an index of refraction of 1.75. What is the critical angle for that substance in air? Go ahead and pause the video and solve this problem. Okay, so let's take a look at the solution. We use Snell's law, n1 sine theta 1 equals n2 sine theta 2. We're going to substitute in the index of refraction for air, which is 1. And we know that this is going to be at the critical angle, so the angle is going to be 90 degrees. So notice we're going from one thing into air. So we're going to go ahead and then solve for theta 1. We know that the substance we're going from has an index of 1.75. So solving for theta 1, we end up with an angle of 35 degrees. If you didn't get 35 degrees, check your calculator and make sure you're in degree mode. In the next video, we'll talk about thin lenses.